So without any ado, my first speaker is my colleague from Databricks, Tathagata, also known as TD. He's an Apache Spark committer, and he has been working with Spark streaming or Spark since the early days when he was a doctoral student at MPLab. So he knows a lot about. He is the guy who actually brought us DStreams, and now he's going to bring us structured streaming, and he's here to tell us what's all structured stream about and what's the magic and why you should care about it. So please give a big hand to TD.
Hello. Can everyone hear me? All right. So thank you very much, Jules, for that introduction. So as Jules said, that I have been working on Spark Streaming for a long time. And so over the last 3-4 years, we have seen the rise of Spark Streaming. It has been very gratifying for me personally. But why Spark Streaming became so popular in the last 3-4 years? Because it fundamentally changed how people wrote streaming applications. So it first introduced the concept that you can use very functional, concise, yet expressive language integrated APIs to write your streaming applications. You don't have to really worry about how it is executed, what are the bolts, which node is it running. You don't have to worry about that. You just express what you want the computation to be, and the Spark will take care of the rest. It also brought in the concept of truly fault-tolerant state management. If you're doing any kind of stateful computation, Spark will manage the state, make it fault-tolerant, and give end-to-end exactly one semantics, even with state. And it also, I think, the fundamental change it brought is that it led to the idea that you can actually build a unified stack which can do both batch processing and stream processing at the same time. Now, and because of that, this is based on reviews from last year, more than 50% of the users in the Apache Spark community consider streaming to be the most important part of Spark. But in the last 3-4 years, we realized that there are some interesting technological trends. Most importantly, that streaming apps are actually growing more and more complex. Gone are those days where where streaming it is sufficient to do things like just for every data item that is coming in, do some small computation and move out. People want to do more complex stuff. People want to do complex computations like aggregations, machine learning algorithms, etc. And the key thing is to understand that we understood is that streaming computations right now do not run in isolations. They have to interact with a lot of other things in the whole stack. You have to interact with batch data. You have to interact with a lot of interactive analysis that people want to do on streaming data. They have to interact with machine learning algorithms. For example, let's understand this with a very simple example. So let's say you have your IoT events coming from Kafka, and this is an event stream. The first thing you want to do, and this is one of the most common use cases, is that you want to ETL it into long-term storage, basically so that you can post-process the data. And here you are concerned about that you want to store every single item. You don't want any data to be lost in the process of storing in some long-term storage like MySQL or HDFS or something. And you also don't want data to be duplicated because of some failure in the system, some data being duplicated. You don't want that. Then as a next step, people may want to do status monitoring of these given data. And there you want to understand how, in real time, how your IoT devices are doing. Are they healthy or not? And here you need to worry about how late the data may arrive, because there may be a time difference between when the data was produced on the IoT device versus when it actually reached the Kafka and entered the long-term storage. So you need to worry about handling delayed data. Then you have to accordingly worry about when you're doing windowing. Let's say if you want to get status like, is my IoT device is healthy in the last 10 minutes? You have to do windowing on the data. That needs to also consider the fact that the data may be delayed. So these sort of things you need to worry about. Furthermore, if you want to go to the next step, people want to actually learn machine learning models in order to do anomaly detection. As your data is coming in, whether the device is healthy or not may not be a simple threshold matching. It may need more complex information like that may require machine learning models to be learned offline and then applied online. And this is again another argument that these applications are not simple streaming applications. It needs to do a lot more complex stuff. And a further next step that people often want to do is actually do it in an online fashion. As data is coming in, the machine learning model is continuously learning and simultaneously applying on the data that is coming in. So to do all of this is not easy. And you need to really think from scratch a whole different paradigm of which is not just streaming. So something you have to think from scratch in a holistic manner. And that's why and to couple with that, there's also that people want to understand this interactively. When there is actually a health issue, people want to go in and actually interactively query that, okay, is this device only healthy or is the other devices also equally unhealthy, and understand patterns interactively. That is again another paradigm that is hard to do with while combining batch and stream processing together. So for this, we need to define a whole different paradigm, and which we call continuous applications. These are applications that are running continuously, combining not just batch, but streaming, slow-moving, fast-moving, all types of data, as well as all types of workloads, batch, streaming, machine learning, interactive analysis, all of them together. And while thinking of this new paradigm, we realized that there were a few major pain points with DStreams. And this is what we have learned based on the whole community reporting us their problems there with DStreams. So for DStreams has enabled a lot of things, but as things are getting more and more complicated, the community is getting more and more demanding in terms of what they want to do. We are realizing that these are the limitations with DStream that we had, because we hadn't originally designed DStreams for those advanced use cases. One pain point is processing with event time. And for those who are familiar with DStreams, they would know that to build DStreams, it doesn't take into account the time when the event was generated in the, let's say, IoT device. It only takes into account when the event actually arrived at the Spark cluster. And so this is this becomes hard to analyze if you want to really care about handling late data and stuff. The second problem that we realize is that even though Spark Streaming had introduced APIs that are that combines batch and stream processing within the same abstraction, but there were still two different APIs which were tied together, but still not quite the same API. And for people who wants to convert their batch applications to run in a streaming manner, they still have to manually change the code from RDDs to DStreams. And furthermore, doing interactive analysis on the DStream data is also kind of tricky. It's not trivial to get that to work. So and the third thing is that it is actually hard to reason about end-to-end guarantees, even though Spark Streaming provided the required hooks to get end-to-end exactly one semantics. It was kind of hard to actually achieve that, configure them in the right way, and actually get that in production while handling things like user changing code. There are failures in the system, failures in external systems, etc. So to deal with these three challenges that we realized with the DStream architecture, we went back to the drawing board and really tried to think what is the best thing that Spark should provide, and what is the right API that eliminates all these pain points and gives the best possible API for the end user to write their continuous applications. And that led us to what we call structured streaming. And this came, basically we realized the simplest way for the end user to build their streaming analytics or continuous applications is for the end user to not have to reason about streaming at all. Reasoning about streaming with late data, etc., is hard. It is not trivial for any person who has dealt with streaming data has gone through these, has realized that this is not trivial. And ideally, the problems that occur over and over again, like handling late data and stuff, the users should not have to worry about them at all. We should be solving them on behalf of the user, and the user should be able to just express their intent on what kind of computation they want, and we should be solving the hard problems of actually dealing with the corner cases of failure, late data, etc. So for this to work, we came up with a completely new programming model. And we said that let's consider your data stream as an input table. Think of your stream as a table that is being continuously appended. So as new data is coming on your stream, every record that is coming in the stream is like a new row being appended to the input table. And so if you basically check on that table every 1 second, we'll call this a trigger interval. So every 1 second, if you check, you will see that this input table is effectively growing in size as new data is coming in. And this trigger is basically how frequent we check. Now, if you think of the stream as a table, then you can write queries on the table pretty much in the same way as you write queries on a static table. Like, imagine your Spark SQL, imagine your SQL queries or your RDD jobs or any kind of batch stuff. You can apply those kind of queries on this ever-growing table. Now, every trigger interval, as the table changes or grows, conceptually, the result would also change. For example, if you're doing a count on the table, as the input table is growing, your count would also change. And that is considered as the result of the streaming query. And then finally, as your result is changing, you want to update, let's say, some sort of external system. Like, for example, you want to basically take your count and keep updating an external MySQL table on the number of records and stuff. You want to output whatever has changed from the result table into the external table, or it could be a MySQL table, it could be some file system or something. And now this model allows you to define, as the result change, what is the output that should be made. It could be either the complete output. For example, you want to update all the counts in the table, in the external table, or an external file system, or you may want to, in which case the whole result table will be pushed out every time in every trigger. Or you could tell the system or tell the model that only the rows in this result table that change, only write them to the external table. Or only the new rows, write them to the external table. So you can define these different kinds of output: complete output, or the delta output, which is only the rows that changed, or append output, which is only the rows that got added in the result table. And the model, the Spark itself would figure out how to exactly define what has changed and accordingly push only that out to the external table. This is what the model allows you to think. Yes, question?
Once you do delta output to a table, would you also be able to take the deltas and then send those as a stream to something else? Like, let's say you had an external database that you also wanted to update, as well as like a Parquet. Would you be able to react to those as delta events too?
Potentially, the model allows you to do that. But as of now, I'm going to talk into in more detail later. Right now, every streaming query allows only one output. In future, we may allow multiple outputs to be simultaneously computed and updated. And the model would allow that. The model would effectively apply to that as well in the same manner. But as of now, in structured streaming, the API allows only one output per query. But now you can actually run multiple queries concurrently in the Spark, in the same Spark cluster. That is, I'll talk about that in more detail later.
Yeah, slightly different question is, can you daisy chain that? Can the output be another stream?
The output be another stream? You could, but it will depend on exactly how the output is made. For example, right now we do not have it, but in future, if we define a Kafka sync, then you could write it out to Kafka and then use another program to use a Kafka source to read that. So all that is completely possible, but it depends on what sources and sinks are defined, which we don't have the Kafka sink yet. We're working on the Kafka source, but more on that later. Any more questions right now on the model?
What sinks do you have?
Right now we have only the file and file as a sink and an in-memory table as a sink. So it'll be in-memory table inside Spark. All right, moving on. So now the key thing is that now that we have defined the model to be a single abstraction of a table, which works for both batch and static data, which means that in terms of the API, we can also define a single API abstraction that works for both batch and streaming. So how many of you are familiar with datasets and data frames in Spark 2.0? Okay, not everyone. Good, I have some backup slides. But for those who are not familiar, the new abstraction that we've not introduced, but we are proposing as the main abstraction now in Spark 2.0 is something called a dataset and a data frame. And I'll go into what that is. And this dataset data frame essentially represents a conceptual table, which may either be static or bounded table, if it is built on a static bounded data, or it can be a streaming unbounded table. Now, what is a data set? For those who are not familiar, it is essentially a distributed unbounded collection of data with a known schema. And by schema, I mean that the system knows what the data in that collection, what is the type of items in that data. For example, is it a collection of integers? How many columns does it have? Is it a collection of complicated JSON structures and things like that? And this is essentially a high-level abstraction that can be applied on any collection. And because it knows the schema, it can optimize your queries based on to be very specific, to be very optimized based on the actual type of data that is present in the data. So, for example, if it knows that if your data has 5 columns, but you only need to read or do aggregation on 2 columns, it will read only just 2 of them and things like that. So it is aware of the contents of the data and it optimizes queries accordingly. And this has a common API across Scala, Java, Python, and R. And to create these data sets, there are multiple ways you can create data sets. So you can either create data sets directly using SQL. So for example, using Spark SQL, you can very easily open up a JDBC connection to a MySQL table and directly give a SQL query, which will return a data set based on the data in the external MySQL table. That's just one of the many examples. Or you can define a data set and from, let's say, Hadoop or S3 or something, define a data set from a Parquet file, and then you can serve that through SQL by exposing a JDBC endpoint and connect your Tableau through it. So you can operate on data sets using SQL, or you can operate on data sets using dynamically typed objects, and they are called data frames. And so these data sets and data frames are interoperable terms. Data frames basically means dynamically typed data set, where and to do that, you have this very RDD-like, but kind of a mix of RDD as well as SQL, kind of a superset of that, a very SQL-ish API by which you can specify programmatically what is aggregation, what type of operations you want to do. And you can plug in lambdas, etc. Those who have worked with RDDs, all of that plugs right in. And so you can, what you get is it is dynamically typed because it is not type checked at compile time. So for those who are familiar with Scala Java, you don't get compile time type safety. But if you want those for even more strict production jobs that should not fail ever, there's a third option of actually defining statically typed data sets. And there you can actually define your Java structures or Scala case classes and stuff, and you get full compile time type safety while getting pretty much the same underlying performance as the other two methods. So basically, in Spark 2.0, this data sets, data frames gives you a whole different, basically a multiple tools to express your computation Either you can write it in SQL, where you get only runtime type safety and analysis safety, or DataFrames, where you get much more safety in terms of syntax errors, but not in terms of actual schema errors, or datasets where you actually get full compile time safety for all your data structures. So you can choose your own hammer for whatever workload you want to write. And this is available for both batch, interactive, and now, as I'm going to talk about, streaming workloads. So to give a brief glimpse of how you would write a batch ETL job using DataFrames, suppose you want to read a JSON file, filter a few items from it, choose a few columns, and write it out as Parquet. This is how the code would look like. You first define, you first read from the JSON file that creates an input data set or a data frame. You'd apply operations on it to create a result data frame. And finally, you can ask the system to write it out, save it in a destination path in the Parquet format. Now, if you have to convert this simple batch ETL job to a purely streaming job, where you are reading data as a stream and writing out continuously, all you have to do is this. You change read to read stream and write to write stream, and say, instead of save, which will do a one-time save, you just say start. And what it'll do is that in the background, your Spark will continuously start reading from a directory of JSON files and writing it out in a directory of Parquet files continuously. While handling things like late data and intermediate errors and stuff, you don't have to write any different code. So you can see that the intermediate code of the result, which expresses the exact computation you want to do, does not change at all. So you can use the same business logic that you have ran as your batch jobs in your, let's say, daily batch job and stuff. You can just convert it to a streaming job without actually changing the logic. What else can you do? So yeah, I've already said that. That all you need to do is change this. So underneath, what the system would do is figure out how exactly the model applies, what is the input table, how is the input table defined on the directory of JSON files, how it changes, and what are the things that it needs to output every time. So all that, this whole model is implemented beneath the covers by the system, and the user doesn't need to worry about that. So let me actually make this a lot more concrete with an actual demo of how this looks like. And everyone can actually run this demo in Databricks Community Edition, which is free for everyone to use. I'm using the Databricks Community Edition myself for running this demo. What Databricks Community, for those who are not familiar, it gives you is that it gives you a tiny cluster for you to start writing your Spark applications interactively on, and it is free for everyone to use. Anyone can sign in and immediately start using it. And so what I have here is, this is the Databricks interface, which has notebooks and stuff. And what I already have is I have attached a demo cluster, which is running Spark 2.0. I'm not sure whether everyone can see this, but it is running Spark 2.0. And what I have here is that I already have some log files written with JSON data inside it in a particular path. And here is, can everybody actually see this from the back? Okay, cool. Awesome. So here I have a path where I have a bunch of JSON files that is already loaded. So let me actually show you what the files are. Oh, my cluster actually, wait. So in the community edition, because it's free, we have a time limit on size a little bit. Okay. So in community edition, since it's free, there is a time limit on the Spark cluster that you can use. So my cluster, if you don't use it for an hour, it kind of kills itself. And if you don't want that, you need to sign up for Databricks non-community edition. So for that, let me actually create the cluster for running my demo. Hopefully it shouldn't take too long. So here, it's actually creating my single node cluster as we speak. Yeah, so to give a little bit tour of what the DataFrame interface looks like here, right now, because it's a communication, I have the ability to create only one cluster, uh, in your actual Databricks, if you actually sign up, you can create as many clusters as you want. You can choose what version of Spark you want, all the way back support from still all the way back to Spark 1.3. You can choose which availability zone and all the fancy underlying AWS stuff that you want is all available here. So in the meantime, while my cluster is being created, it should be done within a minute.
Can you combine like different input streams as part of the structured streaming that you showed?
Absolutely. Absolutely. So hopefully done in there. So my cluster is up. All I'm going to do right now is actually start running this notebook. So let's see what this directory contains.
Is there a reason you picked Scala 2.10 instead of 2.11?
No reason. This would work equally well with 2.10 to 11. So this is the contents of the directory. There are a bunch of JSON files. Let's see what each JSON file contains. So this is like each few lines from the JSON file. It has a time, and it has an action of whether I opened a web page or closed a web page. And so I basically want to analyze how many opens and closes that I have. So first of all, given this bunch of log files, the first thing I would obviously want to do is explore it interactively. And so I first, to explore it interactively, what I have is pretty much similar to the code that I showed you on my slides. I can create a static data frame by just saying that read this as a JSON file and display the contents of it. And what it will do is it will actually read the JSON file. It will actually understand what are all the fields inside the JSON and convert it to a data frame where it knows that there is a time column and there is an action column. And now we can do all sorts of cool stuff on this data frame. And this is running as a batch job, interactive job. So I can extract the time column and define windows of 1 hour on top of it, and which essentially creates another, and then count on those windows, which essentially creates another data frame. And once that I've created the data frame, I can do all sorts of SQL-like stuff. Like I'm actually running a SQL query on this and say, okay, how many opens and closes that I have in my data file. And if I actually have to see per hour windows, this is how many opens and closes that I have for every hour over this time period, etc. So this is all the batch interactive processing. Now, if I choose to actually convert this to a stream processing pipeline, it's actually very simple. Instead of read, all I do is read stream. I'm putting it on the same directory of JSON files and saying that read one JSON file at a time, kind of to treat it like a stream, and then do the same grouping by hour and stuff. And so once I define these streaming data frames, I can very easily do this. I'm going to display this streaming data frame, and what it does underneath is that instead of returning the result immediately, it actually is running a query in the background. And as it's running the query in the background, it's picking up JSON files one at a time. It is automatically and continuously updating the results. As it's finding new files, it's updating the counts. Yes?
If it's reading from S3, is it automatically plugged into the S3 like file system event system to like get these triggers to?
At this point, no. So we have built it in a generic manner with the Hadoop file system APIs. So it works on both HDFS and S3. So right now we are using listing of the files as a way to find new files. It's kind of polling for new files essentially.
The local file system.
It would be implemented in exactly the same way.
It's polling still.
It's still polling. So we implement something that is generic and works for everyone. In future, we may optimize for certain use cases in future.
Probably write because you can rely on the
You could.
So if you have let's say I'm at 17 and I get data from 1.
Mm-hmm.
Will it go and update the original window, like the old window it has written back?
Yes, it is supposed to do that automatically. That's the thing. So the user should not have to worry about updating previous window explicitly and stuff. The system is aware that, oh, the event time is this, so I should put it in the right window. Yes.
If it's writing to an S3 bucket, I think it partitions by like your window function, and so it's constantly adding new files to the S3 bucket. Won't you eventually have the small files problem in the S3 bucket where like the file listing is so large that it can't even like get the file listing?
That is a potential problem. So compaction of small files and larger files is something that the user have to handle explicitly on because that is a slightly more complicated problem, and it is hard to actually handle that in Spark Streaming while maintaining the latency. It's kind of complex. So as of now, it is something that the user has to handle on its own. So what the user can do is that partition the data by, let's say, date. And so as if you know that if data can be at most 2 days old, then the partition directories that are older than 2 days can be compacted away as an additional process by the end user.
Is there a data store where that's less of a problem?
Not that I know of. Okay. So just quick note that it actually walked through all the JSON files, and it has pretty much created the same figure that was in the batch processing, because it has read through all the JSON files, and now it's waiting for, it's still updating, but it'll update 50 times because there are 50 files, and then it'll wait for new files. Anyway, so going back to my rest of the talk, which I need to present again.
So do you have a sense for,
Yes.
do you have a sense for the computational overhead this creates? Because obviously it gives you the power,
Mm-hmm.
but if I do the batch, then I'm running the computation once against the data set, whereas here, I'm kind of running some setup overhead for the small window, then again for the next 5, in this example. So basically the computational overhead seems a little higher.
So let me go through my slides, and if this doesn't answer your question, we'll talk about it afterwards. All right, so I've already showed you how these continuous aggregations work. The API is simple. Let me actually skip a few slides in the interest of time. What I hadn't showed in my demo, and it's actually very cool, is that what this allows, because it's underlying the same API for batch and streaming and the same engine for batch and streaming, it actually allows you to join streams with batches. Like, for example, you can take your Kafka stream, parse it out. If there's JSON data in your Kafka, you can get Spark to automatically parse out that JSON data and combine it and join it with some static data in some other database, MySQL. So this sort of power comes only in a system like Spark, which actually truly unifies batch and streaming and interactive in the same API and the same engine. And you can also, there are more details in the API where you can specify the output mode and stuff. I'm going to skip that in the interest of time. There's another big advantage of structured streaming over Spark streaming is that you can use the same Spark cluster to run multiple streaming queries in parallel, sharing the same resources, and it gives you very strong API for managing these different queries, starting one, stopping one, etc., getting real-time statuses of those queries, etc. So logically, as I've said, and this might answer your question, logically, all these operations are happening on a conceptual input table that is always growing. But it may seem like that the system is keeping track of all the data in the table and continuously computing on the whole ever-growing table. But it's not, because in actually, what the Spark does is that it knows that it is actually a streaming query, and it automatically incrementalizes your query so that it can compute, it can update your counts and aggregations and stuff only by computing the new data that has arrived in the input table. And so Spark takes the job of actually incrementalizing your query, for the job of the user to think about how to run this in a streaming manner, Spark takes over that job and does it automatically for you. You don't have to worry and reason about that. And so in short, this is the high-level thing if you have to remember is that it's a high-level streaming API on datasets and DataFrames that gives all sorts of things, event time, windows, sessions, and unifies batch and stream processing together. And this is something that makes it stand apart from pretty much all other engines because no other engine has a truly combined API for batch streaming and interactive under this using the same optimized engine. And because the API, you can choose your own hammer to hammer your nail. Either you want type safety, you use datasets, or if you want more SQL-like interface, you can use SQL. So this allows a lot more debuggability and performance and ease of development depending on your skill set. And obviously all the benefits of Spark. So for a standard end user, this is probably all that you would need to know. But for those who are more interested in understanding how this actually works underneath the hood, what happens is that, let's take a quick peek, and I'll keep it short. What happens underneath is that there's a Spark SQL engine, which was till now designed for batch queries. And the way it worked is that it used to take batch data frame and data sets and convert it to a logical plan, which is an abstract representation of the query. So if you're doing a filtering, it is the logical plan will represent what is the filter like. And it doesn't really know how to exactly execute it on the data yet. Then there's this magical thing called the SQL Planner, which does all sorts of query optimization, standard database-ish query optimization and stuff that takes that logical plan, does crazy optimization based on the schema of the data, etc., and converts it to an actual physical plan running on Spark's RDDs, which is Spark's low-level API now, and then finally executes that execution plan. And there, at the time of execution, there are other crazy optimizations that's going on, which we have been building over the last 1.5 years. So with structured streaming, this changes significantly. Now the planner, we made the planner far more intelligent that it knows that this is a streaming query plan. And then what it does, it actually, instead of spitting out a one-time plan, it actually spits out an incremental execution plan, a series of them, so that every time there is data, it can run this incremental execution plan on the data that has arrived. So what happens underneath is that, for example, if you're reading data from Kafka, the planner will continuously query Kafka to see whether there is new data in Kafka or not, and it can identify it using Kafka's own offset mechanism to see whether there is new data, new offsets available or not. Whenever new offset is available, it will read only that part of the data, apply the incremental execution plan, and generate a count, and then write it to the sink, let's say HDFS. And this, it keeps doing that over and over again as every time new data is available in Kafka. But, well, that's kind of half the picture, because for doing things like continuous aggregations where you are adding counts over time, you need to actually do another thing. You need to not just compute just the new data, you need to also keep track of the counts that has been updated. So that is what is essentially stateful computation. And what Spark does automatically is it maintains the state in memory, which is backed by a write-ahead log in the file system. You don't need to understand all these details, but the Spark handles all the fault-tolerant, all the details of making it fault-tolerant and recovering from failures, recovering the state from failure stuff. And it maintains the state, and every time there is new data, it takes the previous state, adds the new counts, and keeps updating the state automatically.
At least once semantics, and you'll handle duplicates?
Well, this actually gives you exactly one semantics.
I know, but I'm talking about the Kafka side of it.
The Kafka side of it, if you are writing into Kafka with at least once, so when we're reading from Kafka, we can guarantee exactly once.
Okay, so I can set up my Kafka to be at least once semantics.
Yes.
And you'll handle the rest.
Yes, whatever data is in Kafka, we can read it exactly once. Anyway, so For fault tolerance, what the system does is that every component in every piece in this architecture that I showed, the planner, the incremental execution, the sources, and the sinks, all of that have been made fault tolerant. And so all the metadata and the data that it needs to recompute stuff if there is a failure has been made fault tolerant. So for example, the planner exactly keeps track of the range of offsets that has been read from Kafka in every incremental execution, so that if the planner, the whole Spark cluster and the planner, everything fails, it can read back from that log the exact range of offsets that it was processing and just redo the incremental execution that had failed. Now, if the source, we assume that the sources are fault tolerant by themselves, like Kafka, Amazon Kinesis, files, and so it has the ability to replay based on the offset range exactly the data that would have been read if there was no failure. And the system takes care of exactly figuring out what is the right version of the state as it's updating the state it figures out what is the right version of the state to recover. And the sync, the way syncs are designed is that they're idempotent by nature. And if you write your sync in the right way, it can actually guarantee idempotence. And therefore, together, this whole thing, this offset tracking involved, the state management and the fault transfer and syncs, and can give end-to-end exactly one's guarantee in your streaming pipeline. Yes.
I have two questions. So one is like, does it support the deduping, let's say I'm adding a duplicate data from my streams, and does it support the deduping? Like, can we do it by open source or do we have to it ourselves?
Not as of now. It doesn't support deduping because in the fundamentally, the problem of deduping means you have to keep all the data since the beginning of time, truly. And since Spark is a processing engine, not a storage engine, unlike databases, which is both processing and storing, Spark is not designed for keeping infinite amount of data.
My second question is like, does it maintain the states like between the windows? So if I have 5 minutes window, can I go back in time and look at my previous 5 minutes window?
Exactly, yes. So you can specify, you will be able to, well, not all the APIs have been implemented yet, but you will be able to specify that keep last 1 hour of 5-minute windows and things like that. And the system will automatically clear out old windows and all old aggregates and stuff.
So you cannot replay or like come back. You cannot replay basically the set of events again. So if I have a way, so let's say I'm at, if you're doing 5-minute window, right? If I want to go back 5 minutes, and if I inject the events back in Kafka, it will reprocess them.
It will reprocess them. So yeah, whatever you put in Kafka, it will read it exactly once and process it accordingly. Yes.
Yeah, so the API unification is very elegant, so cool. But how much of the optimizer work has been done? Because like what could happen? So there's the broadcast and shuffle, and then there's the shuffle mechanism for streaming. So it could so happen that when you get one stream window, you get small amounts of data. So in that case, you do broadcast. The next time it surges, and now it's like a big table. So now you're joining a big table with a big batch table. Maybe you have to do shuffle or filtering. And then, so have you taken care of all those kind of edge cases when tuning the optimizer, or is that still work in progress?
That is still work in progress. So we have right now building the basic building blocks of enabling all these operations. In future, we definitely want to do things more crazier, things like cost-based optimization and based on past historical statistics of data and stuff. We definitely want to do that in the future. Can I hold the questions because I'm running out of time? Sudarshan also has to give a talk, so I will be around after Sudarshan's talk for more one-to-one interaction. So let me actually move on. I've just got a few more slides. So I've already said this. I've emphasized this enough. You shouldn't have to reason about streaming, period. So if you want, we have actually done a much more deeper technical dive on the exact semantics and why, even in terms of the semantics, it is different from other systems in our blog posts, 2 blog posts that you should really go ahead and read. We and Jules and we all spent a lot of time writing these blog posts. This is really a lot of plethora of information over there, which you would. And to give a sneak peek from that blog, this is a comparison of structured streaming with other streaming systems that is out there. And one key thing that you would see is that most other streaming systems does not quite handle the fact that they cannot combine interactive queries along and joining with static data, because they are not designed to be a generic streaming plus interactive plus batch system. They are designed to be either pure streaming systems, or at least the engine underneath is designed to be just a pure streaming one. So I can answer more questions on this offline, but I highly encourage you to actually take a look at a blog which would clarify all these. Anyways, the current status is in Spark 2.0, we have the basic API of event time windows, aggregations, append and complete mode, sources, and the files as sources and sinks, and also in memory table. But I will discourage you from actually use it in production, because this is an experimental release. It is still not production ready, but it is definitely worth experimenting with and giving us feedback on the API, on what queries that you would like to see be possible in this APIs and stuff.
So it should closer to a month or a year away
from production. From production ready. So I think it's an evolving process, but I can't make promises. But what I would say is that we definitely want simpler workloads like map-only ETL, where you suck data. There's no aggregation, suck data from one and write it out exactly once into something else. We want that to be production ready by 2.1-ish. Aggregation and stuff, it will take a little bit more time because there's a lot to implement, there's a lot to optimize underneath. So that's what I can say. But again, this is a completely evolving process. Honestly, it moves so fast that we don't really know ourselves that what the state would be 2 months from now. What we are working on right now immediately is we are adding the Kafka source for structured streaming, which should be available either in 2.0.2 or 2.1.0. Again, we still haven't decided yet, but we are working on it right now. If someone is super interested, they can maybe sometime next week they can download it from and compile it from the Spark master itself. Going forward, we are also working on basic things like metrics for understanding how the workload is going on, so that for monitoring and stuff. Stability and scalability, as I said, is our #1 concern, because we want to make it as production ready as fast as possible. Support for more queries, streaming machine learning integrations, all of these are work in progress. So try Databricks, I think my final plug. And with that, this is what all you need to remember for this thing. Thank you very much. You are a very patient audience.
All right, guys, welcome back. Our final speaker, Sudarshan Kadambi. He's the engineering lead for Apache Spark and NoSQL platforms here at Bloomberg. He is a frequent speaker at Spark Summit and Hadoop Summit, speaking about different topics such as distributed infrastructures and performance storage. And today he's going to share about what are some of the challenges about writing Spark applications using online analytics, especially in the case where you actually require a very high level of SLA agreements. So please give a big hand to Bloomberg's Sudarshan.
Thanks, Jules. Let me start off with a poll. How many folks are using Spark in production? How many people are doing Spark streaming in production? Show of hands. Okay, interesting. Anyone doing Spark for interactive queries? Any kind of user interfaces that are being driven by the execution of a Spark job? You are? Are you doing that in conjunction with streaming?
No. Okay. Well, there's a stream engine in front of it, but I'm not using Spark streaming.
Okay, and what user interfaces connected with the? Okay.
Disclosing that one yet.
Okay, cool, very good. Well, you should be proud. All right, so I'm Sudarshan Kadambi. I'm an architect and engineering lead at Bloomberg, focusing on our Spark and NoSQL platforms. In today's conversation, we'll start off by talking about use cases and engineering constraints surrounding data and analytics at Bloomberg. We'll talk a little about the role that Spark plays in it, what it does well, and what challenges remain. We'll talk a little about our approach to serverizing Spark, the so-called Bloomberg-Spark server. And finally, we're going to talk a little about what are the challenges in applying Spark for interactive query serving, which is a personal interest of mine. So Bloomberg is a market leader in providing data and analytics to the financial world. Data management is a core function of what we do. And over the years, we've built various systems and workflows that collect data from various sources, curate it, normalize it, and present it in a form that's easily consumable to our clients. On top of these normalized data sets, we've developed a range of analytics, portfolio attribution and risk modeling, scenario analysis, backtesting, et cetera. There's a whole lot of heterogeneity in the type of data we deal with. It ranges from time series market data to unstructured news content. It ranges from geospatial data, such as shipping vessel coordinates, to graphs, such as supply chain relationships. The Bloomberg platform, and most interesting analytics comes about when you're able to blend one or more of these heterogeneous data sets, and the Bloomberg platform provides our clients opportunities to be able to do such sort of data mashups. For the most part, analytics on the Bloomberg terminal is interactive. Bloomberg screens render in single-digit seconds or less, so the data and analytic backends need to be scalable and reliable. Traditionally, analytics served up on the Bloomberg terminal has been pre-canned. In other words, the analytics is parameterized. Clients are able to specify some model coefficients to influence the results, but can't change the model itself. But we are increasingly in a world where clients want to be able to do ad hoc analytics, often on data sets that are drawn from diverse data domains. So the analytic frameworks that we need to build in the future need to be able to integrate with our diverse data backends. Another aspect is data needs to be fresh and made available to analytics as quickly as possible. Right? So as you can expect, in the financial market, stale data isn't tolerated very much, and there is a constant race to be able to support more sophisticated analytics without sacrificing on freshness, responsiveness, or for that matter, correctness. Some of these use cases are served well by a distributed compute framework like Spark because it allows the analytics to scale up to large data universes. Spark allows for analytics to be expressed against standard data frames, which may be backed by different sources of data, internal or external, with some capabilities for operator pushdown. Thus, Spark acts as a good vehicle for performance systems integration. Spark also provides connectors and transforms for processing incoming streams of data, as we just saw. It allows for intermediate compute results to be cached for interactive query serving. So from a high level, it seems like Spark has some capabilities for online interactive analytics. So let's look a little deeper.
Good question.
I'm going to defer questions until later, if that's OK. So when we started adopting Spark at Bloomberg, we quickly noticed that there are various common problems that everyone needs to solve. Right? So every Spark application needs to connect to some source of data, internal or external. Every Spark application needs to handle reconciliation of streaming updates with some base state. If you're having interactive Spark application, you need to serverize the Spark context. Right? So you need to be able to set up a server that accepts requests, triggers some Spark job and responds to it, gets the results, and then sends back a response. But more importantly than any of this, building vertically isolated Spark applications results in siloed analytics. Right? So everyone talks about data silos. We believe that analytic silos are just as toxic. So we wanted to build a standard runtime which provided some constructs that allowed reuse of analytics across different domains. So the embodiment of all of these objectives is what we've ended up building. It's called the Bloomberg-Spark server. This particular presentation is not a deep dive of the Spark server. I'm only going to be talking enough about it to motivate the rest of the conversation. We've given a fairly detailed presentation about the Spark server and its capabilities at the Spark Summit back in June, so I'd certainly refer you to that talk. So within the Spark server, application developers implement their business logic within these request processors, which get deployed and hosted within these Spark server instances. So you can think of each request processor as a Spark application that is coexisting within the same Spark server instance and shares the Spark context. The Spark server itself maintains the Spark context, and this is essentially the driver application, and it's associated with a large pool of executors running somewhere on the cluster. Developers also register datasets at these endpoints, whereupon the framework uses schema and some additional metadata to generate and bootstrap data frames and make it available within a registry. Right? Since the lifecycle management of data is handled by the framework, we call these managed data frames. In some sense, you can think of the Spark server as a servlet container of sorts, but specialized for Spark applications. Right. So within this managed data frame registry, you have a bunch of managed data frames. So each managed data frame represents a data set. Within each managed data frame, you have a set of data frames that are constantly being created and destroyed. Each new data frame represents the latest and greatest snapshot of a given data set. So just to summarize, Bloomberg datasets are represented as managed data frames within the Spark server runtime, and each managed data frame contains a sequence of data frames with newer data frames in the sequence representing a more up-to-date snapshot of data. And the Spark server provides a toolkit of ingestion methods that a dataset owner can choose to have their datasets updated within this Spark server runtime. Right? And request processors, which, as I said, are business logic implementations, request for a set of managed data frames from the registry. They perform some transformations, and when done, return them back to the registry. So the Spark server has many capabilities, but one of it is particularly relevant to the rest of today's conversation. Right? There's a significant long tail to how Bloomberg clients access our data. Typically, only a small fraction of the data is used in majority of the analytics. So not all data records are equal. Right? The low latency nature of our Spark analytics often means that we cannot afford the data retrieval and data deserialization costs from an external backing store. So high-value records are kept deserialized within Spark. So our framework allows dataset owners to specify arbitrary filters at the time of dataset registration, and these filters are applied to figure what records have to be extracted from the backing store and kept within Spark. To illustrate with an example, let's say data pertaining to companies that are members of the most popular equity indices, S&P 500, Dow 30, Russell 3000, should be kept within Spark. For everything else, we would go to the backing store. Right? So let's say for a given data set, the subset criteria is that the company should be a member of the S&P 500. When a query comes in that represents a data universe that is the S&P 500 plus one company, our framework applying predicate logic can figure out that, hey, for 500 companies, the data has been cached within Spark. There's just a single company for which I need to go get data from the backing store. It rewrites the filter automatically and pushes it down as an efficient point lookup. All of this is completely abstracted away from the end consuming application. So the gist of it is to achieve high performance, we are caching substantial state within the executor JVMs. What is the implication of doing that in terms of high availability and online analytics? So that's going to be the focus of the rest of this conversation. Right. So let's review a little bit of theory before we go any further, just to be on the same page, in case the knowledge of Spark internals is mixed in the varied in the audience. So the basic abstractions of state in Spark is an RDD. The resiliency of an RDD comes from the execution lineage, which is preserved in the driver. So if RDD partitions are lost due to executor failures, the lost partitions are reconstructed by replaying the lineage, as we know. Along the way, another form of resiliency that was added to RDDs is through RDD replication. I believe TD wrote some of this code. The Spark API provides various levels to control the persistence of RDDs. So some of the persistence levels include memory only 2, memory and disk, and so on. So for example, memory only 2 means that for a given RDD, partitions are replicated in memory on 2 executors. So RDD replication ensures that if you lose an executor, the partitions that were there on the lost executor are still accessible from other executor instances. Right? So another aspect is for online analytics, there is no distinction between system unavailability and query slowdown. So we tend to see them as the same. So what capabilities does Spark have to address query slowdowns? Right? So to address the issue of straggler tasks, Spark supports the notion of speculative execution. So if certain tasks are running slow, Spark can proactively schedule execution of those tasks at other executor instances. And whichever set of tasks completed first, the output of that gets used. Similarly, for online queries, another hit to performance can come from garbage collection pressures on the executors, especially if there is a substantial amount of data being cached within the executors. However, yet again, Spark's push to have both execution and storage memory move to Java off-heap should address this significantly. So when looked from top to bottom, Spark seems to provide reasonable capabilities for providing highly available access to the state that is cached within Spark. So what kind of gaps might exist? So let's go a little deeper into the theory before we understand that. So Spark is a master-slave application. You have a driver, a bunch of executors. So references to RDDs are held within the driver. And in this instance, you have an RDD with 2 partitions. The contents of the partitions themselves are on the executor, but the references to the partitions are held at the driver. I'm going to be talking about RDD blocks and partitions interchangeably. There are some nuances, but for this conversation, it's a valid simplification. So an RDD block equivalent to an RDD partition, right? So within the executor, these RDD blocks are held within this component called a block manager. So every executor has a block manager instantiated within it. And the executor communicates its state to the driver over this RPC environment, which is constituted of a bunch of actors, the block manager master in the executor, and the block manager master endpoint in the driver. So now that we understand who the players are, let's try to understand how do RDDs get stored, how do they get replicated. So RDD computation happens at query time lazily, right? So if you wanted to persist an RDD and keep it around for interactive query serving, you would cache the RDD and then call count on it, which would run the entire transformation pipeline associated with that RDD and then to trigger its materialization. So RDD computation happens by the driver telling the executor, compute the partitions of that particular RDD that are held at that executor. If you had said that I want a persistence level of memory only 2 for that particular RDD, the executor computes a particular RDD block, and then it realizes, hey, I need to make another copy of this RDD block. So the executor sends a message to the driver saying, hey, give me the list of peer block managers. So the driver says, here you go. Here are the list of peer block managers. So then the executor randomly picks peers based on the number of replicas you want to make. And then it transfers the computed block over to the chosen peers. And then it notifies the master saying, here's where copies were made. Right? So once all of the executors have completed the block transfer and have notified the master that, here's where the copies were actually made, the fully replicated RDD is now available to the next phase of the computation. So this is how RDD replication works today. So what are some challenges associated with the way the replication scheme works today, right? So at Bloomberg, we run Spark on Yarn, which is the resource manager on Hadoop clusters, as everyone knows. And the way Yarn works is it launches containers on various nodes of the cluster. And the executors, JVMs, are instantiated within these containers, right? The driver itself may or may not run on the cluster. Mesos works in a very similar manner. The way Yarn launches containers, there may be more than one container that's brought up on a single node, and hence more than one executor brought up on a single node. So if you had said that I want 2 copies of my RDD blocks, it's possible that the 2 copies ended up on the same node. This makes this susceptible to node failures, which we would like to protect against. Similarly, perhaps we want to go a step further and say we want to protect against rack failures as well, right? But more important than either of these is the fact that lost RDD blocks are not proactively replenished. So what does that mean, right? So if you initially said, I want 2 copies of my RDD blocks, and then an executor or 2 went away and got replaced by other executors, over time your replica count is approaching 0. So this is a problem for our Spark server use case, wherein we want to be able to serve up interactive queries against cache state with consistent latencies. Clear so far? So to address these capability gaps, we've done a bunch of implementation under the Jira 15352. This Jira has already gone through some extensive community review, thanks to Eric Liang and Reynolds Zinn from Databricks for a lot of the PR review. The ideas and the implementation were by Shubham Chopra, who's on my team in New York. All of the credit for this work goes to Shubham. So what's the idea here, right? The first concept is to introduce notions of topology awareness into RDD block replication. So what is topology, right? Topology is how is a node physically located within a cluster, and how does it wire up to other nodes in the cluster, right? This implementation was done in a bunch of phases. The first thing was to make the replication scheme pluggable. Right? Once the replications, and we provided a default implementation. Once the replication scheme is pluggable, clients can, or users of this API can provide custom replication methods. We provided a default implementation which preserves the current behavior, which is a random replication. The next step was we modified the RPC communication between the driver and executors associated with RDD persistence and RDD replication. Right? When an RDD block is computed, the executor sends a message to the driver saying, hey, give me the list of peer managers. We still preserve that sequence. But what has happened prior to that is the driver gets the topology information of all of the running executors. So it does this by a topology mapper interface that we introduced. And we provided a default implementation of this topology mapper, which uses a topology script of the same sort that HDFS uses for rack awareness, if folks are familiar with that. So now when an RDD block has to be replicated, the executor connects to the driver and says, hey, give me the list of peer block managers. The driver sends over the list of peers, but this time annotated with the topology information. And the executor now uses a prioritizer to select the list of peers to replicate to. So we were thinking about how should we implement the prioritized peer replication. There are a number of objectives one can think of depending on the topology. I don't want more than one copy in a single host. I want at least another copy of the block on the same rack. I want a third copy of the RDD block on a different rack, and so on. So we ended up implementing a generalized constraint solver of sorts, wherein you can specify a set of replication objectives and a list of peers. It tries to find the minimal set of peers that satisfy those replication objectives. We then ran some simulation studies to study the convergence time of this solver on clusters with up to 100,000 nodes. At this point, we are fairly confident about the robustness and performance of the solver. There are ongoing conversations to contribute this to core Hadoop in addition to Spark. Another thing that was done is to provide hooks in the driver to catch executor failures and proactively trigger replenishment of blocks that were there on the lost executor. This is done by contacting other executors who have copies of the same block and having them initiate a block transfer to their chosen peers. Right, so we provided this implementation. It was done fairly quickly. We're pretty happy. Executor HA worked pretty well before we started this, and this patch has made it even better. So have you solved all the problems associated with HA in Spark for online analytics? So I previously mentioned that resiliency of the RDD comes from the execution lineage. The execution lineage is preserved in the driver. Right? What happens if your driver goes down? Right? So you could have a 1,000 executor cluster that's primed with state meant to address queries in a very low latency manner. But if your driver goes down, all of that state dissipates. Right? Yes, you could bring up a new driver. You could bring up a new set of executors. You could repopulate all that state within those executors. But by then, you've missed your query SLAs. Right? The issue of the driver being a single point of failure for online analytics has many solutions. Unfortunately, most of the solutions are also incorrect. Right? It's a very tempting proposition to simply run multiple instances of your driver and load balance client requests between them. Right? The issue is the state of the data frames referenced by those drivers, driver instances might be slightly different because they correspond to different snapshots of the underlying data set. So the results would be inconsistent if you simply load balance requests between the two drivers. Right?
Do you want to talk about the infrastructure, like what you implemented, how big is your cluster, how many events do you process?
Sure, I'd be happy to talk about it offline afterwards. So let's consider a strawman solution to this problem. Right? So what is the problem? You want to achieve high availability for your state, but you don't want to sacrifice consistency. So what could you do about it? So here you're running multiple Spark servers concurrently. Each Spark server is associated, as I said, the Spark server is a driver application, so it's associated with its own pool of executors. It's a full-fledged Spark cluster. And the Spark cluster is constantly being hydrated with the latest snapshots of various data sets. Previously, I mentioned that results would be inconsistent if I simply load balance requests between these Spark server instances. So what we're doing here is running them in an active standby configuration by doing lead election through something like Zookeeper, right? So only the active Spark server serves requests. The standby Spark servers, all right, so if a client connects directly to the active Spark server, it accepts the client request, it runs some Spark job, gets the results back, and sends back the response. If a client connected to the standby Spark server, it simply forwards on the request to the active Spark server. So the standby Spark servers are keeping themselves warm. They're doing all of the background refresh process to have the latest and greatest snapshots of various data sets. This way, the standby Spark server can take over and become active at a moment's notice without any expensive state bootstrap. Is the solution clear to everyone? Does anyone have any questions? All right. So why is this a strawman solution? This seems to work great. Why is this not the end state, the desired end state, right? The issue is we've ended up using as many resources as it takes to run n Spark servers, right? So as I said, a Spark server is a driver and a set of executors. So you have these standby Spark servers, which are in some sense doing busy work. They are keeping themselves up to date, but they're not able to participate in processing of client requests. You have the active who's working really hard, trying to keep up with the request volume, but he's not able to tap into any of the resources that are in use by the standby Spark server. So perhaps we can do better. Right? Right, so what does it mean to have HA of the Spark driver? Right? So the Spark driver is an arbitrary Java application. So what does it mean to have HA for literally a black box Java application, right? So not all the state within the Spark driver is interesting or is even expensive to reconstruct. We are specifically interested in those RDDs and data frames that are being created by the ingestion workflows, predefined ingestion workflows within the Spark server and are kept around for interactive querying. Right? In fact, to further reduce the scope of the problem, we can focus on data frames as opposed to RDDs in the sense the transformation pipeline or the transformations expressed against a data frame can be captured as a very succinct logical query plan, which can be serialized and moved around, as opposed to transformations on RDDs, which are in the form of bytecode, and so a little bit more cumbersome to work with. So to summarize, the state that we want to preserve are the data frames that are being kept around within the Spark server for interactive queries. So before we talk about HA of the state, let's talk about what is the state within the driver. Let's catalog that state. Right? The driver state includes the block mappings, what blocks are held on what executors. The driver state includes the cache manager. The cache manager is a component from Spark SQL wherein it maps the signature of a logical query plan to the data frame that resulted from the execution of that query plan. Right? So this way, the next time a particular Spark job was submitted and it resulted in the generation of a logical query plan or a superset of it, it can look up that logical query plan by its signature within the cache manager, and then retrieve the data frame and reuse it for that portion of the computation. Right? So the driver state includes the cache manager. The driver state includes the scheduler queue, the state of the jobs, the stages, tasks, etc., associated with the Spark context. And lastly, the Spark driver tracks the hostname and port of the running executors. As we point out, there's a bit more state. This is not an exhaustive list by any means. So what would be the benefits if we were able to catalog and capture all the interesting state and then persist it elsewhere? Right? We would be able to protect against driver failures even. Right? We would be able to bring up a new driver which quickly reads this particular state. It already knows where the running executors are. There is no need to restart any executors. There's no need to repopulate any state within those executors. We might even be able to run these drivers in an active configuration if the state store that you're writing to provides some recipes for synchronization. Right? So one solution is these data frames or RDDs themselves can be moved off heap off executor into some distributed in-memory store, Tachyon or Ignite or Geode or one of those solutions. And any residual state within the driver, once the data itself has been moved off executor, any residual expensive state within the driver could perhaps be externalized in some state store like Zookeeper, right? So this is one way to go, right? But what if we went in a different direction? So what would it look like if Spark natively supported state-preserving driver restarts, right? In this solution, you have multiple Spark server instances. Even though it's not indicated on the diagram, they do run in an active standby configuration. So this is exactly like our strawman proposal that we had discussed a couple minutes ago. The only distinction is that these drivers are associated with the same pool of executors, right? So let's say you want to generate an RDD that you want to keep, or a data frame that you want to keep around for interactive query serving. That particular transform comes to the active driver. That results in the computation of some RDD blocks that are stored in some set of executors. Once the RDD block is computed, we had discussed how the executor communicates that state back to the driver, saying, hey, yes, I have computed this RDD block that is available on me now, and perhaps a couple other copies that I have made. What's to stop the executor from communicating the state to another driver as well, right? Similarly, when it communicates the state back to the other driver, what's to stop it from sending along the AST or the logical query plan that resulted in the generation of that data frame over to the other driver? This way, both drivers are aware about the existence of that block in that executor. Both drivers within the cache manager have the mapping between the logical query plan to the data frame that resulted from it, right? So what would happen if you had a solution like this? Let's say the standby Spark server went away. The active Spark server went away. The standby can become active at moment's notice. It already is associated with the same pool of executors. It already has all of the state that links those RDD blocks together. So it has all the information. It should be able to start processing client requests at a moment's notice, right? This is a design proposal. We have not implemented it yet, right? So what is the point of presenting that in this meetup? The idea is something like this is architecturally invasive. It requires a fair degree of community conversation and consensus. So one of the points of bringing it up in the meetup is to socialize the proposal and to collect some feedback on how feasible it would be to get something across. I strongly believe that for online analytics, these sort of architectures are the right way to go, and we'll continue to push for it. So in summary, today we looked at what it takes to do. We looked at some aspects of online analytics with Spark. Streaming is another very interesting component to it that we didn't cover in today's talk. So Spark is a pretty capable framework. It has an expressive API. It has useful higher order libraries. But I think online analytics is just beyond the boundaries of what it can do well today. But I think with some community effort, it should be possible to extend Spark to encompass this area quite well. So before I end, the Spark team at Bloomberg is engaged on a number of pretty exciting problems. It ranges from our serverized Spark runtime for financial analytics to evolving core Spark infrastructure like we saw today, to making Spark work better with the Jupyter notebooks for data science workflows. There are a number of initiatives we have taken up. There's a need for quality engineers, so we are actively hiring. So if any of these problems interest you, do reach out to me, and we can talk further. Right. Thank you.